Suppose we want to observe and monitor the activity of an asteroid located above the ecliptic plane of the Sun. To do that, we can send a spacecraft in the asteroid's location. However, a spacecraft that is powered mainly by chemical thrust is not that useful, as the velocity needed to reach the asteroid is so high that a large amount of fuel is needed. So, is there a better alternative? Enter the solar sail. A solar sail is like a sail, except that it is not cruising the waters, but it is traveling in space. Unlike using the wind to propel itself, it uses the momentum transfer of the photons as a source of thrust. By making the solar sail's area as large as possible, the solar radiation force becomes large enough for it to continuously accelerate, thus gaining large speeds. The solar sail's orientation, defined by its cone and clock angles, can be controlled, generating trajectories that can't be obtained using typical gravitational forces. The controllability of solar sails lets us construct a family of paths. Depending on the mission, we need to choose the path that best attains the mission's objectives through the process known as trajectory optimization. Usually, for solar sails, the best path is the one that minimizes the time to reach its target. So how do we choose a trajectory that minimizes the flight time? In general, flight time trajectory optimization is so difficult that we resort to using numerical approaches in obtaining the optimal trajectories. However, for very special cases, we can obtain closed-form solutions with the help of a pen and a paper. We can find the best trajectories using semi-analytic means. These semi-analytic methods are the ones we employed in this work. One semi-analytic method that we proposed is the surface constraint approach, which is a set of steps that we follow to design a family of trajectories. For instance, let us constrain our sail on a cylindrical surface. Assume that the cone angle is always a constant, while the clock angle is a function of the sail's polar position. Using these conditions as inputs in our surface constraint approach machine, voila! The trajectories of the solar sail are obtained. But why cylindrical surface in the first place? Well, using this constraint, one can obtain a transfer mission towards an asteroid with a highly inclined orbit. Based on our results, a solar sail can thus reach asteroid 2008 SB85 in less than 600 days. Yay! To learn more about our work on solar sail trajectory design and optimization, please attend my dissertation defense on the 7th of June 2024, 3:30 p.m. See you there!